Hello everybody. So now we are going to discuss one point which is more of a chemistry thing, but it's something that we see a lot in our chemical engineering applications, which is the types of reaction. And it's well known that the reaction can be either reversible or irreversible, and the irreversible reaction means that the reaction goes in one direction, which is the forward direction. And if we have this reaction A plus 2B go to C and 3D, then the arrow is just one arrow in one direction. So it's forward reaction, it's an irreversible reaction. For the reversible reactions, the reaction goes in both directions, in the forward direction and in the backward direction. And in this case, if it's the same reaction, then the arrows are two arrows, forward and backward arrows. And one thing that we know, or we said before about the irreversible reactions, that the reaction stops when the limiting reactant is consumed. This is the point when where the reaction will stop. However, in the reversible reactions, we don't have this option, or this is not how the reaction stops. The reason is we have reaction going in the forward direction and the opposite reaction is happening in the backward direction. So in the beginning, you have a lot of A and B, and then the reaction goes quickly in the forward direction until the C and D concentrations of C and D increase, and then the backward reaction starts. So all the time we will have A, B, and C, D. You have the four components together in the reaction mixture. So this is one thing that we cannot avoid. It's the nature of reaction. So the reaction will reach a point when the concentrations are constant. And the concentrations are constant not because the reactions stopped, but because the rate of forward direction reaction is equal to the rate of backward reaction. So the number of moles that are consumed from A and B equal the number of moles of A and B that are produced by the backward reaction. So it seems that there is no change, but it's called the dynamic equilibrium. So this is the point when the reaction will not change, or the concentrations will not change. This is what we call the equilibrium. So the chemical equilibrium is something that we really care about, because we need to know how far the reaction will go, because we cannot exceed the equilibrium conversion. There is maximum conversion of A and B that we cannot exceed, because this is the nature of reaction. This is thermodynamics. This is nothing we can deal with. We can tweak the conditions of the reaction to force the reaction to go more forward, but still we will be limited to the equilibrium conversion. So the parameter that we can use to know or to relate the concentrations in the reactants and products in case of equilibrium is called the equilibrium constant, which has the symbol uppercase K. And let's say we have the reaction A plus B go to C and D, and it's a reversible reaction. Then the equilibrium constant equals the concentration of products, the multiplication of the concentration of products, YC multiplied by YD, over the product of the concentration of reactants, which is A and B. Of course, this is a very simple case. We have different equations to express the equilibrium constant. There are different types of equations that we can use, different concentrations like partial pressures, like molar concentrations, like different things. So these are all ways of expressing the equilibrium constant, but in this course, because this is more of physical chemistry and thermodynamics or chemistry, which is not something that we are really interested in going into the details of. It's out of the scope of the course, so we are not going to go into more details. What we will do is just solve this example, which is a nice example to understand this thing more, and it relates to what we discussed in the previous video about the extent of reaction. So it's going to be really helpful to see this. So we have this reaction between carbon monoxide and water producing carbon dioxide and hydrogen, and we assume that the reaction proceeds to equilibrium at temperature T in Kelvin, of course, and the mole fractions of the 4 reactive species satisfy the equilibrium relation that we see here. So this is the equilibrium constant related as a function of the mole fractions. And we know that the temperature is 1105 degrees Kelvin, and at this temperature K equals 1. So we know that the value of K is 1. And we know that the feed contained 100 moles carbon monoxide, 200 moles water, no carbon dioxide, no hydrogen, and the reaction comes to equilibrium at 1105 degrees Kelvin, and we need to know the equilibrium composition and the conversion of the limiting reactant. So let's put the givens that we have first and then see. So I'll solve this example using the two ways, using the table where we put the feed reacted and out the product, and we will solve it using the extent of reaction, and you'll see that the results are exactly the same. It's the same thing with little differences. So this is the reaction, this is the feed, 100 carbon monoxide or kilomoles of carbon monoxide, 200 of water. The tricky part here is that we don't know how much is consumed or how much is produced. And for all the examples that we solved before, we knew how much of specific component is either consumed or produced. And in this case, we can know how much is reacted, and we can calculate the rest of the parameters. In this case, we need to know how much is reacted. We don't know. What we know is that the equilibrium constant is equal to 1. That relates the mole fractions. So this is going to be a little tricky. So what we will do is, since we don't know how much is reacted, we will assume that the amount of carbon monoxide that reacted is X. We don't know how much is this X. It can be 10, it can be 20, it can be 50, it can be 100, I don't know. And this is what I want to calculate. So this X is the amount that is reacting. Of course, it reacts with, it's 1 to 1 to 1 to 1, so it's all the same number of moles, and the product is going to be 100 minus X, 200 minus X, X, and X. Now, if we go back to the equation, it is a relation between mole fractions. It's a relation between mole fractions, not number of moles. So I have to calculate the mole fractions of all the 4 components in the mixture after the reaction is done. So these are the products, the number of moles of the product. So the mole fraction is number of mole over the total number of mole. So we will calculate the total number of mole, which is 100 minus X plus 200 minus X plus X plus X, which is 300 moles. And now we can divide each one of them by the total number of moles. So this is the 100 minus X over 300, and the same 200 minus X over 300, and the same for carbon dioxide and hydrogen is going to be X over 300. And now we can substitute in the equilibrium relation, which states that Y carbon dioxide over Y hydrogen multiplied by Y hydrogen divided by Y carbon monoxide multiplied by Y water equals 1. So if we substitute with these equations here in this equation, this is what we are going to get. So it is X over 300 multiplied by X over 300, which is hydrogen times CO2, divided by 100 minus X over 300 times 200 minus X over 300. Of course, all the 300s will cancel. The rest is just math. We will expand these two brackets, and then we will have this equation, X squared equal X squared minus 300X plus 20,000. And we can simply calculate X to be 66.67 moles. And if we know X, then we know the number of moles of the product of carbon monoxide and water and all the components. And we can calculate the mole fractions of each one of them, which are these numbers here. Okay. So it's pretty simple. It just needs some imagination how we can start by putting this X here. Now let's see if we use the extent of reaction to do the same calculation. So we will put the same givens here, that the number of carbon monoxide in, the number of water, number of moles of water in, and the stoichiometric coefficients. And let's see. So I want to put the mole fractions. and the mole fraction in the equilibrium constant equation, and the mole fractions are equal to the number of moles in the product over the number of, or the total number of moles. So what we will do is we will calculate or write the formula for the product number of moles of in the product for the 4 components. So for carbon monoxide, it's going to be number of moles of carbon monoxide N plus the extent of reaction multiplied by the coefficient. Carbon monoxide is -1 and the feed is 100, so it's 100 plus minus 1 multiplied by xi, so it's going to be 100 minus xi. For water, it is 200 minus xi. For carbon monoxide, it's going to be N, which is 0, plus 1. Now, because this is a product, so it's going to be plus xi, so it's going to be xi, and the same for water, it's xi. And we can calculate the total number of moles, which is going to be 100 minus xi plus 200 minus xi plus xi plus xi, which is 300. So now we calculated all the mole fractions by dividing each one of them by the total, and the rest is going to be exactly the same thing. The only difference here is that we put xi instead of x. The rest is exactly the same. It's the same problem. If you look at this here and you look at this here, it's the same equation. Exactly the same equation. Just x instead of xi or xi instead of x. And we will get the same results at the end. Okay. And again, this is why I love this method. I didn't have to put any symbols for anything. I'm just using the equations. You calculate the extent of reaction, you know everything. And this is what is beautiful about this method. So I'll stop here and we will continue next time, inshallah, and I'll see you there. Goodbye.